Hey, how it's going, guys? In this video, we are going to look at the mixture of experts or MoE, right? One of the most hot topic when it comes to training large language models in the current world of AI. It's going to be a crash course on MoE. I'm going to cover everything, and I don't expect that you have any basic knowledge also about MoE. So this is for beginners. This is for anyone who wants to understand about mixture of experts or MoE in detail. So let's jump in and see, what MoE is all about. So if you look at here on my screen, we want to first, of course, cover a few things theoretically to understand about MoEs. Why do we need it? And of course, the mathematical intuition behind it. Gonna go and cover the code, and of course, in the end, we're gonna create our own MoE from scratch in pure PyTorch. We're not gonna rely on any kind of libraries to kind of build it. So that's what it is, guys. Here, right now, let's see what we're gonna do here. So, okay, excuse me. Let me just come back here. And there are a lot of models which are already developed using MoEs. All these current models that are being rolled out from these bigger companies, they are somehow relying on mixture of experts model, because not all the tokens are being active at the given time. It based on your queries, etc. It activates certain tokens, or basically activates the speciality tokens, or so on and so forth, right? So that's what we're going to look at here. You can look at this Mistral AI mixture of experts paper, and we're going to cover Mixtral, the model that I trained last year, I think, about using MoEs. And then we'll also look at merge kit a little bit, that how you can also combine different LLMs and build your own new model. But let's first see, what it's all about. Now, let's say, you are kind of going into a hospital. Let's say you are going into a hospital, right? And you will find out when you think of a hospital, when you think of a hospital, what do you basically think, right? About speciality. A good multi-speciality hospital will have, different things. Like it will have, for heart disease, if somebody has any issues with their heart, they will visit the cardiologist, right? Cardiologist section. So that's called cardiology or cardiologist, right? And if somebody has fracture, or let's say a bone related thing, right, they will visit an orthopedician. So I'm writing here orthopedic. So they will visit the orthopedician. So orthopedic is there, orthopedic surgeon. Or let's say if somebody is having cold or a viral fever, because currently, we have been seeing a lot of viral fever like issues in India or South Asian country because of the weather and the climate. So let's say if cold is something there, then you will just visit a physician, right? That's what we're gonna do. I will come to code in a little bit. I also have code snippet to explain that each and everything. But think this MOEs as like this, instead of one doctor, knowing everything superficially. There are the treatment is better when you kind of, or when each expert handles their own speciality. So that is very similar, right? MOE brings, when you talk about MOE in layman terms, I just wanted to give you an analogy here, that MOE basically means the term of specialities. Okay, so not term of speciality, that's the wrong statement, team of specialities for your and receptionist. So receptionist is nothing but the gatekeeper. I will talk about it, the gating mechanism. So team of speciality plus a receptionist, an idea to AI. So that's what the fundamental thing when you talk about it. So here if I write MOE, right, in context of AI, it's an idea basically where we have team of speciality, and I hope I am writing it correct, or specialist plus receptionist, because receptionist is also very important, which basically receptionist will guide, the patients or whoever is there, to the right doctor looking at all the symptoms. Or this can also be, uh, this can also be junior doctors, basically, if I say so, in bigger hospitals. So this is what it is currently. It's basically, in that was in layman terms, but if you talk about, in the AI world, or the AI term, is basically, a multiple experts neural networks. That's what it is, a transformer. Okay, so here I'm writing that. Okay, so let me just write it here. Or multi-expert or multiple expert neural network. That's what it is, in that. And then this has a gating network. So two things, a neural network with multiple expert neural network and a gating network. So these are the two things combined that routes the input basically. So let's say when I have an input, that gating network will route the input to the multiple experts neural network, or the specialist one, of course, in this case. So if I just come here and write that, okay, let me just write it here. We have a traditional giant neural network. Let's say earlier when we used to train LSTM or RNN, right? Earlier we used to train these models, right? Let's say earlier we had uh, CNN, ANN, whatever you name it, right? RNN, etc. Any kind of, or even a simple perceptron, or any kind of neural network that we used to train a giant, like let's say the giant neural network here. So I'm writing giant NN. Now, they were basically jack of all trades. They were not specialist in certain domains. So that's the problem. Now MOE is basically a specialist and the gatekeeper that decides who handles the case. So I hope you got in very layman terms that that's the idea of the definition of it. Now the question is, why do we need it? That's the question. So let me just come here and write it here. Why do we need MOE, or mixture of expert? So that's the right question, that why do we need MOE? Because see, the thing is, I like to break down the conventional or traditional neural networks. What are their constraints or the limitations? The number one is the high computational cost. So I'm writing here high computational cost, high computational cost of traditional NN. So that's the NNs I'm writing. That's the issue, because double computes, your electricity bill, your carbon footprints, and everything. Your carbon footprint is also very important when you talk about sustainability, right? So that is something is there, and the limit. One of the most uh, found limitations of traditional neural networks is the inefficient learning, right? So I'm just writing here inefficient learning. So inefficient learning of traditional, this will remain same. So traditional NNs, like training one network for all tasks, right? Means parameter, interferences across all the tasks or across tasks, which is not good enough, in today's world of, how are we training models, and lack of deep expertise. So traditional NN, they kind of lack this. So I'm writing here, like, let's say traditional NN lacks like deep expertise. They are like really shallow, right? So they don't have deep expertise here. So like shallow, the broader knowledge, they don't have in-depth, like very poor domain specialization. So if somebody asks you in interviews that why do we need MOEs, what are MOEs, in simple terms, this is how you have to explain it, and we'll deep dive into the code, from scratch actually. So two key components you have to remember if you talk about the architecture of MOEs, right? Let's write it. So I'm here writing, let's say, architecture of mixture of expert. Fundamentally, we are talking right now. We'll go deep dive very soon. Now, simply there are two that you have to remember: expert network. So I'm writing like this: one expert network and one gating network. These are two fundamental components. And this is really important for you to understand. Expert network is a multi-specialized sub-networks, basically. That kind of math, literature, coding, history, geography, they understand these things. And gating network is a small net that decide which experts to activate. Okay, so these two are like fundamental things that you have to understand. But how it's work, right? The working process, which is important. So let's go into the working process. Okay, like how is the workflow when we enter a question? So working process of MOE. So let me just write it here. The working process of MOE is how it works. Just give me a moment here. Yeah. So let's say there's an example. So let's first start with an example here. So I'm just writing the example here. And this is going to be like my input. Let's say you have built a chatbot, and you will have an example. Like let's say what is the quadratic, like let's say I'm asking a math question here, so that will be easier for me to explain. What is the quadratic formula? Okay, we have studied these quadratic equations in our high schools, right? Even before that. So what is the quadratic formula, right? Let's this a question. I'll just give you a complete walkthrough on high level that what is the working process of MoE, how does it start? The number one thing that you have to remember, in this process is like this. So number one is input and vectorization. I'll just change the color here. I needed something dark. Yeah. The number one is input and vectorization. That's the number one thing, input and vectorization. Like, if I just also go, let me just keep little space and keep writing, and then I'll come back to each pointers later. So input and vectorization is the number one thing. Then gating network that I talked about, we have to assign some weightage. So I'm just writing like this: gating network, assigns weight. This is the number two thing. And if I just keep going, number three is top k expert selection, like how many experts we want to select. For this, when we are coding also, we'll keep it to one or two at max, just to code it on a limited compute. But this is very important, top k like expert selection. So top k expert selection is the next thing that happens. That is 1 2 3. The number 4 is your experts runs in parallel. So I'm going to write expert runs in parallel here. And the last one, the number 5, weighted aggregation. We have to aggregate the weight, right? Weighted sum basically, or you can call that, yes. So we aggregate the weights, so weighted aggregation. So these are the 5 points that MoE working process works, and this is so important to understand. So here I'll just write that a bit more so you can get that completely completely you understand this process. So number one, I just talked about input and vectorization. Now it's feature vector stores. Basically, it's a feature vector store that shows the math signals, right? So let me just write here. So these are basically your feature vectors, so your strong math skills or math signals, basically. Not skills might not be a good in this term. Yeah, this is not a good word to explain. It's basically a signal for the gating network. So that's the one thing. So when that is done, the next thing is gating network that has to assign weights, right? So let's say here I write, in this case, when we ask the question, and we'll understand this through formula also when we are coding it, that how does it really make this weightage kind of a thing. Basically, it's like, again, a softmax will come in play here. So if you look at this, the probability logits. Now, if you look at this one, getting network assigned weights, let's say in the question that we have asked here, what is the quadratic formula? Here it's a math thingy, right? So let's say it says, okay, 0.85 math, and programming goes to the 0.15. So that basically assigning the weights. Now let's say here I have top 2 chosen, top k expert selection, because it might have tens of experts, right? So top 2 chosen for this task. Now experts runs in parallel. So math expert gives formula, let's say, because we have 85%. So here I'm writing math experts give formula. That's the number one thing. And programming expert shows the Python code, because here we are asking, let's say, the programmer. So programming expert gives the Python code for that particular formula. So this is what it is. And the last one is weighted aggregate. Basically, it's a final blended output. You can say that. So in a very simpler terms, final blended output. And guys, these are very important to understand. Trust me, agents and all are really fine. Okay, but when you really want, you see this companies like Meta AI and OpenAI and Anthropic, Google, they are paying millions dollars, to these people, researchers they are hiring. They are not normal people who does LangChain, LangGraph, how to create agents. They have deep understanding of each of these components and each of these steps. They understand these processes, how to pre-train models, how to train foundational models, how to do inference, post-training, research, so on and so forth, right? So this is very important for you to understand these things rather than only focusing on relying on tools, because even eventually in future you don't need those things, right? Even AI will kind of, whatever you are building agents and all, even there are tools which will build agents automatically. Just give a prompt. It's still happening, right? There are a lot of things already available. You should understand how to build an LLM from scratch and those kind of things if you need a deeper understanding, right? So this is important. You don't need it, of course, but if you have an ambition or an aspiration to work for such companies, you have to go deep dive, right? It's really important. So keep that in mind. Now let's go into the numerical example here. Now I'll just go into the numerical example quickly, right? So let's say we have a setup. So I'm just writing the setup here. And this is basically a simulation of what we are thinking. So let's say we have a setup. And in the setup, we kind of write like, let's say four experts. Let's say we have four experts into 1 million parameter each. So this is how I'm writing. Four experts are there and 1 million parameters each. All of these experts that you see have 1 million parameter each, right? And then there is a getting network. So then we have a getting network. And let's say getting network have a 10K parameters. Because getting networks will always be small. They will not have like the same kind of a parameter that the experts are having. Getting network is a small network. So let's say it's a 10K parameters. And then we have top two selection out of the four experts. So this is a numerical understanding that I'm showing you. So let's say I'm writing implement a sorting algorithm in Python. Now our query is, so let's select a query here quickly. So our query is implement a sorting algorithm in Python. Okay, so I'm just writing here in Python. And you would have solved a lot of lead code questions like this, right? Now let's say implement a sorting algorithm. How do we kind of how does it, okay, let's come to the getting here. So let's say our getting is very clear here, as so far you would have understood, because this is a programming question. So here programming will be 0.8. Let's say I give a weightage, and this weightage how we assign, we'll see is a probability value actually. Now programming 0.8, and we give math kind of, let's say 0.1 or something, right? Now this is my getting value. So how much compute we save, guys, here? So if you look at the compute saved value for these things, right? Traditional, if you look at traditional one, very common sense, right? Traditionally, we have 4 million. So let's say I'm just writing here, traditional, we have 4 million params. And now MoE, if we have a mixture of experts, how much we're going to have? We're going to have 2 million plus 10K. And there are few other computes, like there are few other, tokens that are involved. We'll discuss that. So let's say I'm writing here 2.0 million active. So almost 50%, right, that we save on just on the tokens. So this is very important to understand. And benefits, you can see the benefits. I don't have to probably write the benefits. There are benefits. Let's write the benefits here. So benefits are clear of MoE. So the first benefit is pretty much for me efficiency, because when we are training, when we are of course creating models and then we are letting it for like deploying it for inference, which is really important to have MoEs based models where we know we are really efficient, right? Only a fraction of parameters runs per query, which is very important. So efficiency is the first thing. Then we have expertise. So expertise is the first thing, and then we have scalability, right? So it has to be scalability, and then we have parallelism. So it can run in parallel. So these are the four things that we have to understand. Benefit of MoE, uh, benefits of MoE, why do we need MoEs, and so on and so forth. So there are a few real world MoEs we have to understand. One is the first one that I came to know, of course, was the switch transformer. I don't know if you're aware of it. Let me show you that quickly. So if I just open here switch transformer, you can also go through the paper if you want, right? Switch transformers was like amazing. You should read this paper, guys, by William Fiddles and Barrett Joff. You can see it from Google, right? It's a one. I think it's in 2021 or 2022. It's I think 1 point some million parameters, and I think there were 2,000 plus experts were there, and it was 7 times faster than the other models that Google has, like T5 for example, because T5 is one of my favorite model at that time, I'm saying. So now I have learned a little bit, so kind of gone through that phase. But switch transformers, check it out, amazing. 5 or 6 trillion parameters, if I'm not wrong. And you can see it says 7x increase in pre-training, then T5, you can see it over here. Yeah, that's what I said, right? Across that one. So that's really important. The other one that if we talk about, there are a few. So let me just write it quickly here so you can just follow along. I'll give this link, right, of this PDF. We'll get that in a PDF. That's the one thing. The other thing is like, if I talk about real world MOEs, so real world MOE is like switch transformer is one of my favorites when it comes to MOE, because I read this paper before, preparing for this tutorial video or the crash course, because I was reading this paper, understood a few things and how they did it. It's by Google actually. You can see all the Google folks. Okay, I'm writing here, excuse me. I'm not looking at the monitor. And then there was one more model by Google. I forgot the name. It's LAM or GLAM or something. So you can check it out. I'm just writing here like something like GLAM or something. Okay, you can check that out. And then we have our Palm 2 is also based on MOEs. Okay, there is backbone is MOE. It's multilingual and multi-domain. And the backbone was MOE, of course. It's again by Google. And the latest one, like which got really good hyped, of course, is Mixtral 8x7B, which came in 2023, 2 years back. So this is the model actually, Mixtral of expert. This is the paper. You must read this paper if you want to understand about MOEs, guys. Okay, you can see Mixtral 8x7B based on MOEs, same architectures, blah blah blah. As a result, each token has access to 747 billion parameters. So you can find it out here. So that is amazing. Now they have code also available and the web page is also available. Now the question is, okay, then MOEs are really good, right? Then why not the entire world is working with MOE? So MOE also had its cons, as right, everything has its own pros and cons. So if you talk about the pros and cons here for MOEs, let me just write it here, right? Challenges. So challenges will be the right word. Challenges of MOEs here, right? So if you look at the challenges of MOE, the first thing here is load imbalance is a very big challenge when it comes to MOE, because fundamentally you have to see the load balancing loss, because your data might be really biased. Expert might go biased on what it's learning, right? Fundamentally, it's a fundamental problem of how we train artificial models, right? Artificial neural networks. So that is something that to look at that. The other one might become a challenge is the communication overhead, right? If I use the right word. So let me just write it here. Oh, I'm not sharing my tab screen here. Uh, excuse me. Communication overhead, because that can be fixed with expert parallelism over across GPU. So we'll have multiple GPUs. So I have to fix the parallel thingy that we have. So load imbalance, communication overhead, and the last one is memory use. Because see, your X2, I wrote it wrong here. Well, it has to be active, so we'll discuss about it. Okay, so there is memory uses. It's not that it's really less memory uses, so you can understand that as well. Now, future directions, if you talk about what are the futures that people are talking about, so the people are talking about different types of MOEs, hierarchical MOEs, cross-model MOEs, personalized MOEs, dynamic expert selection, so on and so forth. These are coming on with the new research paper that you have to read, right? So understand that, okay, we understood. Okay, it's basically, if you just look at from the top also here that we talked about multiple expert and NN here, when you talk about this, it's just like small. Let's say here, if you write, if this is the right things to write, it's like small MLPs, like multi-layer perceptrons, the transformer where, this feed forward layers. Now we are going into the code a little bit, so we'll talk about this terminology. The feed forward layers that we have in the transformers are like replaced by the small perceptrons, or the small MLPs, or whatever you call it. They are the experts actually. Now I'm talking the real technical thing, because so far I was giving you an overview. Now the tiny router or gates that we talked about for the gating network, they look at each token and they say, okay, each token, and I only activate the only top K experts. Now this capacity keeps huge, but per token compute is like very small. So that is what it is. Now the origin is very back. Okay, we talked about Google switch transformers model, but if you go back, it's like from 1990s. Okay, so there are a lot of papers that you can read about it. Okay, that's what it is. So you have to keep in mind, guys, it's not that easy also, because all experts must be live in memory. Okay, let's say you have your compute, right? You have deployed your model somewhere which is based on MoE's backbone. Now all your experts has to be activated and it has to be in the memory. So that is a big challenge, right? Uh, so even if you look at this paper, if I talked about this one, which is 8x7b, right? It behaves like a 47 billion, you can see it, it says has access to 47 billion parameters, but only uses 13 billion active parameters during inference. So keep that in what I'm saying, each token. So it's 47 billion dense model for the VRAM, so your GPUs, right? So it's not that also easy. So when you are running it on a small GPU, you have to be careful about these models. Okay, like the bigger models, you can't do it. I can go a little bit on the mathematics, if that makes sense, right? But that will go a bit difficult. So we can basically look at some of the code thingy here. So let me just give you a code walkthrough here. I'll just bring up my tab screen here again, and we're gonna go through the code thing. So let me just bring that code quickly here so I can explain that to you. Okay, so here is my code image that okay, where did it go? We can't see it. Okay, now you can see it. So here I have a simple, okay, let me just make this a bit bigger here. Okay. Now, if you look at this first one, right, this is pretty simple. Here we have one small MLP. So this part that you see, it's a small MLP that we have. So I'll just write on top of it, a small MLP, multi-layer perceptron, right? It's an expert, in that case that we have. So I'll explain that, in step by step. Here we have top one router class that you see. If you see this class, top one router, okay, that's what we have. I think you can see that. Yes. And then we have MoE MLP. If you come down here, and we're going to talk about this part here, MoE MLP. This basically uses the router to send tokens to experts and enforces a capacity limit per experts. And that's what it does. And we're going to look at that, and combines experts output with router weights and returns and loss. Of course, returns a loss, which is an auxiliary loss, to add to your task loss. That's what it does. If you look at in the end. So we're going to talk about that. Yeah, you can, if you look at the, yes, that makes sense. Capacity per expert, which is here. Bucket tokens by expert. Yeah. So let's go through that in step by step. And yes, so first line is pretty straightforward. Import torch. This one that you see, okay, which is like, as I said, right, we're gonna do it in pure PyTorch. So it's basically the module-based class of PyTorch for your neural network thingy, and it has a NN functional offs like softmax and GLU and whatnot. So that's what it does. So I'm not that gonna go and in deep. Now, if you look at this one, it defines a two layer here. So it's defined two layers, right? It's a two layers feed forward, or FFN or MLP, whatever you call it, block for a single expert. So that's what we are doing here. I cannot make this more bigger. I think this is the biggest size of this image to kind of embed in this tab. So if you look at this line, you will understand nn.linear, right? And that's what it does. Now, that's on the two layers that you see. FC1 is basically that you see is self.fc1 projects token hidden size. That we have D model and D hidden that you see, and then we have a D hidden D model projects, FC2 projects that back D hidden D model, which is basically respects the transformer dimension. So there's a simple small MLP that we have. And then we have one more defined forward self x that you see, one more function, forward function is basically the forward pass. So I think little bit of transformer knowledge is required, guys, to understand this. I will recommend you watch my videos. I'll give the link in description, how you can create your own transformer like LLM based on transformer models from scratch. So if you look at this, it says it's a forward pass, and we are using GLU, which is for non-linearity. So GLU non-linearity between two linear layers that we have defined on top. So that's what this does. Now it's basically shapes. If we talk about the shape, basically if x is n and d underscore model, like let's say output is n underscore d underscore model, which is your list, of course. So this is what it is. So that is the first class that you see, expert MLP. Now we have a switch style router. This one that you see. So top one router is a switch style router, by the way. So let me just write it here. So it's a switch style router. Now in this one we have, so router is just a linear classifier. Okay, very simple. Okay, if I say so. So it's a linear classifier over your experts. Okay, there is no non-linearity when it comes to routers. Okay, it's a linear classifier over experts from token embeddings to n experts logics. That's what it does here. So if you look at here, it says n experts, n experts. So this line that you see, I just made it. I hope you can see it here. Oh, you cannot see it. Okay, now you can see it. There's a bit of network problem because I have connected my external tab with my monitor, and that's an issue, but that is fine. So now, if you look at this forward function, which says forward self-extraining true, where we have flattened tokens and router probabilities, what this does, it comment the state shape. That's what it does. Like, we flatten the batch per time into a single token dimension. That's what we are doing here. If you look at this reshape thingy here, B into T and then D, n equals to B into T. That's what we are doing. So you can route the tokens independently. That's what we are doing here, okay, in this part. So pretty straightforward. Now if you look at this logit self dot pros n, which kind of got a bit hidden, okay, I'll just go a little up. Yeah, basically that compute the router logits per token over your number of experts that you have. That's what this does in n and e that you see here, okay, this part. So this is what it is. And then we have converts logic also that you see here with prob. This part that you see f dot softmax convert logis. It picks the single based expert, this top one weights. Now if this is important, top one weights that you see line code, and of course we'll go through this code also on Colab notebook. We're going to train a model, but the top one weight that you see, it basically picks the single based experts per token. It's a non-differentiable selection actually. If we talk the technical terminology, and that's what it is. It's grab the probability assigned to the token, the assigned to choose the expert for each token. That's what it actually does. This becomes the mixture weight since k equals to 1, right? It's just a scalar per token. That's what it is. So I think we are good. So far, we're gonna go into the code and understand that. But before that, I'd like to explain that MoE MLP, which is important. It basically builds the router. This part that you see here, it basically builds your router. So it's builds the router basically, and a bank of number of expert. So this is what I'm writing here, bank of experts or number of experts, MLPs. Here, the very important thing that you should read for, like latest, I was part of an interview, and I kind of witnessed something which I was taking an interview actually. The cap factor is very important, right? That you see this cap factor. Now cap factor basically controls the per expert capacity. Okay, that's called cap factor when it comes to building this. Like max tokens per uh, ex, expert per token, yeah, per batch. Actually, that's the thing, that's the right thing. Max tokens per expert per batch. That's what it does. It basically controls the capacity of each expert, or per expert is the right thing. It prevents one expert from getting all the tokens. That is the cap factor. That's very important when you are building MOEs, right? So keep that in mind. Okay, and yeah, I think that is fine. We're gonna go into the code. We have some other things that probably we can understand. You can read about it. Is more is like, one is capacity enforcement, where we are doing here with XC, this value that you see here with this part, we do capacity enforcement. If too many token wants like a particular expert, we have to drop the extras here. So that's also important. You can see expert forward weighted output. This is important. We'll go through the code on Colab and understand that. So let me just go through the Colab now. and show you how we can train. This will be available for you to guys go and check it out. I I wanted to cover the mathematical intuition, but there is no single formula when it comes to like MOEs. It will become a math class. Okay, if you want to kind of talk about it, if you want to talk about mathematics, maybe I can drop a note through a Notion template or something. But there is a core formula that you have to understand. Like the core formula, if I write it for router, so the formula that you see mathematically, okay, very quickly, we're going to just write it here. I also don't remember it for now, but there are a few components that we have to understand through mathematically. One is the router. So the router is important, right? The getting thing that we talk. So the router getting formula is very simple. Let's say we have jet of t, so jet t, right? And then we'll have wg. I have written it over here for because I don't remember it. xt, and then yeah, this is how we define it. Where you have to keep in mind that pt is like softmax of jt, where we calculate the softmax function using softmax function of this, and then this becomes this. This is the formula of mathematically, this is the formula of the router. Then we have expert, that's a different formula. So it's there's no such a single formula. There's a canonical MOEs math that we can do it here, but that will require that video will become really lengthy to explain each and everything. The only thing is that pt of e that you see here, this part is the router's probability weight, as I said, right, for expert e. Let's keep that in mind. And then you can talk about MLP's formula, then you can talk about dense MOEs, classic outputs formulas. So there are not a single formula. Then we have sparse top K MOEs formulas, etc. So it's not a single thing. I don't want to make a math class, but yeah, maybe I can give a Notion formula sheet for this. You can just go through it and let me know what do you able to find it. So what I'm gonna go next is show you this MOE crash course. I have to reconnect. There's a notebook, very well commented, so you can just figure it out here, right? So I'm just gonna show you how we can train. I'm gonna train an MOE on a very simple data, which is a Shakespeare's text that I'm getting it from GitHub, which is on character level. But you can improve this, of course, and of course, this will be a task to you if you want to improve it. Okay, we can definitely improve that. Let me just reconnect. I'll just run this for now. Okay, let me just run this for now. Yes, perfect. All right. So few things before that. Okay, there are different ways to build MOEs, guys. Nowadays, I wanted to show you how to build it from scratch. So I'll show you that. You can also use Merge Kit by RCAI. RCAI is really doing good when it comes to, of course, large scales model training, for enterprises. So they are doing good. You can look at Merge Kit. I have created this model called Mixtral, which is a medical MOE. You can see it says a medical MOE is developed through the amalgamation of three leading models: Mistral, Meritron, and MedAlpaca. It has been downloaded by thousands of people so far. Okay, and you can go and try it out here. It's on my Hugging Face account. You can see this is my Hugging Face account, and you can see there are 24 models. You can find out where did it go. I think I have to click on View More Models, kind of to check that out. Yeah, this is the model. You can see that. So to try this out as well. Okay, and of course I'll go back here and MOE and look at it. So we have a config class for this notebook. We are running this on Google Colab T4, which is a free GPU given by Google Colab, so I'm using that. On this config class we have use MOE true, set false if you want a day's baseline. If you don't want an MOE, you can just do it. I want to build it a modular notebook, that's why I have commented it like that. We have a number of layer 6, number of head 8, dimensions 512, dense MLP hidden. You can see 2048, etc. Also used for export, vocab limit, block size, etc. Use all characters because it's a small data set. We want to use the entire character of that txt file that we want to load. And we have some other configs. Now this is important. Number of experts are 4, but here we are only keeping top K1 switch style. We don't want to keep it more, which will require more compute to do that. And we have a capacity factor. I talked about cap factor, if you remember in the formula. So in cap factor where I explain that, which is important. So let me just bring that here. This is the cap. If you look at here, I talked about this cap factor, right? Capacity thingy. So that is coming here. So we have a cap factor. So keep that in mind. We have load balance coefficient called LB coefficient. You can find that again, here in this formula. You can find it out here as well. It's not clear right now, but we can make it clear. It will take a little time to Now it's clear. You can see the LB loss and LB coefficient if you go up and read that. So this is what it is. And yeah, we have Z loss coefficient, set 0 to disable outer Z loss. Yeah, so this is what it is. And then it makes sure that we are running it on a GPU machine in the last. So that's what we have. If you look at the config here, right? Okay, just let me just do CFG here and see what happens. It will show an object or what? Yeah, you can see it's an object. That is fine. Now here we are loading the data that's called tiny Shakespeare data sets that we have here. You can see it's from Karpathy, is one of my idol when it comes to learning all of these things. I really like him, follow him a lot. I recommend you also do that. If you look at here, Karpathy character RNN master data, he has input.txt. We are getting that through URL library, URL lib module, okay, and we're just getting the text and so on and so forth. Okay. If you just fetch something, it will just get that same thing 200 times. Okay, there's a fallback I have because sometimes it doesn't connect. So if you look at this, we'll be able to get the text here. First citizen, before we proceed any further, hear me speak, blah, blah, blah. Okay. Now characters, it's a character level data that we have. I'll recommend you do better. Don't do it on character level. We just should keep it, you want to keep it like that. In the vocab size, you can find it. So it's very small data, guys. It's not a trainable thing, but I want to show you that. So let's just keep going. Data in, we are doing the encoding. The first thing, we get the feature vectors. You can see the tensor value. Here we calculate. If you just print that, right? Let's print it. And you can find out the numbers here, right? Train data. Just we split that. You can see get pretty standard forward. Now you can see we have an RMS normalization here using the NNN module, right? So we have a forward pass. You can see it over here. Pretty much, if you know transformer, you have to know transformer. There is no other way. And you can see we have a causal attention thing going on here, a self-attention layer here with NNN module. Okay, and I'm skipping this because I want you to watch my transformer video, which is pretty detailed. Go and watch that. Okay, you can see here we have all the projections, KVs, etc. And we have a forward pass again. Okay, you can see we're using PyTorch HDPA. You can use Flash kernels if you have like recent CUDAs. I don't have it, if I'm not doing it. But yeah, if you have it, feel free to do it. This is our expert MLP that we discussed. You can see the same thing, the same code that I was showing you here. So if I just go a little up on my tab and show you, you can find out the same MLP that we have here, expert MLP that I explained, two-layer forward pass, with the small MLP. We have the same thing over here going on. So let's just run this. And then we have a top one router. Again, the same thing that I discussed, class top one router. And here we have in the same thing that I explained there. So let me just get that in quickly because it's going to take some time. And then we have the same, MoE MLP that I talked. If you just go a bit up, excuse me, you can see it over here, right? MoE MLP with the cap factors and whatnot. Everything is here. You can see this cap, this is how we are calculating it. It's an integer value and we're getting it self dot capacity factor n per self dot n experts. This is amazing, right? So this is what we are doing, a dense MLP, and then you have the transformer block. So let's just run this, and we are creating a tiny GPT class where we just blend all things together. So we just use the class tiny GPT, and we just initiate the model here. When you click on the model, you can find out in this model, right? It's an entire model pipeline. It's called tiny GPT token embeddings. You can see it over here, 65 and 512. 65 was the vocabulary size, right? I guess pretty small, but you can find it out here. Block 0, of course, RMS norm. This is fine. RMS norm. Block 1. This is cool. You can see here the MLPs, a very tiny, small MLPs. Expert, fantastic, right? This looks good though. Okay, just go up and just AMPs, that is fine. Where we get the data type for the models, you'll find out, oh, we have BF16, that's amazing. Okay, and then we have just bind that model to that, all the data types to that model. That is fine. We get the optimizer. It will take a little time for the optimizer. And if we are using Adam W, you can see here with all the parameters. Looks all good. Learning rate, weight decay, maximize, this is fine. Count parameters. It's gonna create, you can see the total parameters, only 38 million parameters. Using MoE is true, number of experts 4, active experts per token 1. And now we have the training loop here with the cosine thingy. Let's just run this model train. and now we are training. So it's going to take a little time. You can see the first step, and so bad. Okay, we have a validation loss of 4.41, guys. So 4.41 is like, you can see I have written it below also. The perplexity is E for E square. Uh, yes, and that value, validation loss, yes. So E for power 4.41 is like 82, of course, and that is too far too high, right? As it's written here, you have your perplexity value has to be lower, so then your text fluency will be higher, right? The randomness basically. So now it's coming down. You can see on step 50 we got a bit half of it. So even though we will have a perplexity score of like, let's say 40, so perplexity score of 40 is also very high. We should have perplexity score of like 8 to 10 or 15 or whatever, to reduce that. If you give it more steps and more better tokens, it will of course shape up. So it will generalize better. So keep in mind we are having only 65 vocab size, so not that good. So you can turn it for longer. You can train for longer and longer steps, and of course you can log this less also if you don't want to see the verbose. You can just increase the CFG step to like, let's say 5,000. Okay, so you can do that. Right now it's I think 500 or something. I haven't seen it. So that is what it is. So it's not recommendable, and you can keep the estimate loss like iterations also, like 5 or something, and print every like, let's say 100 steps or 200 steps, and you can do that. So that is some of my recommendation, but you can see it's training right now. We are training our own MoE simple from scratch in pure Python. We haven't used any like libraries or something framework to do that, because this is how you learn. Okay, this is how you learn. This is how you'll do your own things. I'll give this, of course, to you in video description. As it's happening, I'll show you a agentic AI toolkit that I have created. This toolkit is for you if you want to master agentic AI. This toolkit contains 150 plus N10 workflows. Every week we am pushing more workflows into it. It has 3 months skill roadmap. A lot of people ask what is the roadmap to learn AI agents. You get that. You will find it in this in this kit. We have some of the frameworks, toolkits, methodologies for use case selection, success frameworks like KPIs, risk management, governance, and so on and so forth. You'll find out this in this entire agentic AI toolkit. I'll give the link so you can try it out. This is how the N10 workflow agents looks like. 150 plus agents, and you can find out there are 152 to be precise. You can find out all these N10 workflows. So I'll give the link in description. Check it out. Now you can see we have around 400 steps. Okay, and learning validation loss is like, that's fine. Doesn't look that good. 2.45, let's say. And let's say I have a context. I want to get the output. So let's get the output. Model.generate. And you can see it's so bad. Okay, it says Romeo, hi, as a fat tip, but it generates character, nothing surprising, right? Because you have to do it for more steps and on, of course, more steps and a little bit on higher token size as well, because this is pretty small. So make sure that you increase better tokens. Okay, so you have to do that. But it's a good learning experience if you want to find it out, learn that. Check it out, Merge Kit also. I recommend you check out Merge Kit by RC. Okay, they have a web UI also through Hugging Face or something. You can find out here through RC app. Yeah, here I think on this space you have to go and check it out. Hugging Face Spaces, you can go and check it out, but you can also do it yourself. You can just do pip install thingy and you can just get it done here. And read this paper, guys. This is how you enhance your understanding. I'll give this PDF also, and this switch transformer paper also if you want that link in description. That's all, guys. This is what I wanted to show in this video. I wanted to cover MoEs, mixture of experts, from beginning. That will help you in interview. That will help you if you are doing some research. That will also help you if you're training your own MoEs, in some capacities. If you like the like the video, hit the like icon. If you haven't subscribed yet, please subscribe the channel, guys. That motivates me to create more such videos in near future, right? Uh, that's all for this video. Please share this video and the channel to your friends and to peer. That's all. Thank you so much for watching. See you in the next one.